Welcome to Learn with us. This is the fourth lecture of Basic Electronics.
In your previous lecture, you studied about electrical networks and components of electrical circuits. In your last lecture, you also understood what is Ohm's law, what is voltage divider rule, and what is Kirchhoff's current law. Now, what are the learning objectives of this lecture? In this lecture, you will understand what is Kirchhoff's voltage law, what is current divider rule, what is Thevenin's theorem, and what is Norton's theorem. Now, what is Kirchhoff's voltage law? Kirchhoff's voltage law states that the algebraic sum of all the voltages rising are equal to the sum of all the voltages dropping in a closed path. It is given by this equation. It is showing the sum of all the voltages that are rising in a closed path, and it is showing the sum of all the voltages that are dropping in a closed path. Usually the direction is clockwise. Kirchhoff's voltage law also states that the sum of voltages around any closed path of a circuit is 0. It is denoted by summation V equals to 0. As I have just mentioned that usually clockwise direction is used, so this direction is represented by this arrow. So this is Kirchhoff's voltage law. If we have a circuit like this is a battery which is connected to resistor 1. This resistor 1 is connected to resistor 2, and this resistor 2 is further connected to resistor 3 in series. Now this is the positive terminal of the battery and this is the negative terminal of the battery. This is R1, this is R2, and this is R3. Since R1 is connected to the positive terminal of the battery, so this terminal of R1 is positive, this is negative, this is positive, this is negative, this is positive, and this is negative. The voltage drop across R1 is V1, the voltage drop across R2 is V2, and the voltage drop across R3 is V3, and this is the direction of current. Okay. Now how we are going to make KVL equation? We will consider alternate terminals here. We'll start from battery, like we'll start from this point. So we'll write minus V plus V1 plus V2 plus V3 equals to 0, or we can also write this equation like V minus V1 minus V2 minus V3 equals to 0, and this equation can be rewritten as V equals to V1 plus V2 plus V3. Here this V is telling us about voltage gain, and these V1 plus V2 plus V3 are representing voltage drop. Now here we will look at one example problem. Now look at this circuit. As you can see here, the battery is providing 30 volts and there are 3 resistors that are connected in series, and the voltage drop across each resistor is 10 volts. As you can see here, minus 10 volts is representing voltage drop across R1, R2 and R3. Now, how we are going to make KVL equation here? Again, we will consider alternate terminals. This is the positive terminal of this battery. This is negative terminal. This is positive terminal of R1. This is negative terminal of R1. This is positive terminal of R2. This is negative terminal of R2. Positive terminal of R3, and this is negative terminal of R3. Now, we will write the equation as minus 30 plus 10 plus 10 plus 10 equals to 0, or we can write this equation as 30 minus 10 minus 10 minus 10 equals to 0, or 30 equals to 10 plus 10 plus 10, which is further written as 30 equals to 30. Now this 30 is telling us about voltage gain, and this 30 is telling us about voltage drop. So this is Kirchhoff's voltage law, which states that the algebraic sum of all the voltages rising are equal to the sum of all the voltages dropping in a closed path. Here we will look at another example problem. I am going to draw one circuit here. This is resistor 1, and the voltage drop across resistor 1 is 4 volts. This resistor 1 is connected to one voltage source of 36 volts. This is the negative terminal of this source, and this is the positive terminal of this source. So this terminal of R1 is negative and this terminal of R1 is positive. Now this voltage source is further connected to resistor R2, and the voltage drop across resistor R2 is V2. This is the positive terminal and this is a negative terminal. Now this voltage source of 36 volts is further connected to R3, and this is positive terminal, this is negative terminal, and the voltage drop across R3 is 12 volts. This R3 is again connected to another voltage source of 14 volts. This is positive terminal, this is negative terminal. Now again this is connected to another voltage source Vx. This is positive terminal of Vx and this is negative terminal of Vx. So this is your circuit and you have to find Vx. So how you are going to analyze this circuit? You will look at both of these loops. This is loop number 1 and this is loop number 2, and now you are going to make KVL equations for each loop separately. First we'll look at loop 1. Here we'll start from this resistor R1, and again we are considering alternate terminals here. So the equation will be 4 volts minus 36 volts plus V2 equals to 0. So it will become minus 32 volts plus V2 equals to 0. Therefore, V2 is equals to 32 volts. Now we will look at loop 2. The equation of this loop will be minus V2 plus 12 volts plus 14 volts plus Vx equals to 0, and we just calculated V2, which is 32 volts, so the equation will be minus 32 volts plus 12 volts plus 14 volts equals to minus Vx. By solving, we get Vx is equals to 6 volts. So this is how you are going to find unknown voltages using Kirchhoff's voltage law. Now what is current divider rule? It is the method to find unknown current of any element connected in parallel. It is used when there is no clue of voltage. Now look at this configuration. Here there are two resistors that are connected in parallel, and we know that for resistors that are connected in parallel, R equivalent is calculated as 1 upon RT is equals to 1 upon R1 plus 1 upon R2. After simplification, we get RT is equals to R1 R2 divided by R1 plus R2. This is your equation 1. From Ohm's law, we know that V is equals to IR. Therefore, Vt is equals to It multiplied by Rt. This is your equation 2. Now, we'll put this value of Rt from equation 1 into equation 2. So, we'll get Vt is equals to It multiplied by R1 R2 divided by R1 plus R2. Now, what will be the equation of Ohm's law for resistor 1? It will be V1 is equals to I1 R1, or I1 is equals to V1 divided by R1. Now, we know that in parallel circuit, voltage remains same. So, it means Vt is equals to V1. Now, we'll put the value of Vt from this equation A into this equation B. So, we'll get I1 is equals to It R1 R2 divided by R1 plus R2, and this is divided by R1. Now this R1, it will cancel this R1. So we'll get the final equation, which is I1 is equals to It multiplied by R2 divided by R1 plus R2. So this is the equation of unknown current across resistor 1. Now, what will be the equation for current across resistor 2? It will be I2 is equals to It multiplied by R1 divided by R1 plus R2. So, these formulas are for only two resistors that are connected in parallel. In our previous slide, we derived CDR formula for two resistors that are connected in parallel. Now, if there are three or more resistors that are connected in parallel, then how you are going to find unknown current of any element? Now look at this configuration. Here there are 10 resistors that are connected in parallel. First, we are going to calculate R equivalent. We know that it is calculated by 1 upon RT is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 till 1 upon R10 for this circuit. Now after solving, we'll get the value of R equivalent. Now again from Ohm's law we know that V is equals to IR. Therefore Vt is equals to IT RT. Now we know that in parallel circuit voltage remains same. It means Vt is equals to V1 is equals to V2 is equals to V3 is equals to till V10. Okay. Now current through any resistor is Ix is equals to Vx divided by Rx. Again we know that voltage remains same in parallel circuit, therefore this equation A, it can be written as Ix is equals to Vt divided by Rx. Now we'll put this value of Vt from this equation 1 into this equation 2. So we'll get Ix is equals to It RT divided by Rx. So this would be your CDR formula for 3 or more resistors that are connected in parallel. It means you just have to calculate RT first, and then you have to write the value of Rx in this formula. For suppose if you want to calculate I1, then this formula will be IT RT divided by R1. And for I2, here Ix will become I2 and Rx will become R2. Okay. Here is your class task. Can you find I1, I2, I3 for these 3 resistors that are connected in parallel when IT is 10 amperes, R1 is 10 ohms, R2 is 25 ohms and R3 is 100 ohms. Take 5 minutes to complete this task. Now, if you take the time to compare these two divider formulas, you will see that they are remarkably similar. Note that the ratio in voltage divider formula is individual resistance, that is Rn, divided by total resistance, whereas the ratio in the current divider formula is total resistance divided by individual resistance. Now we will look at Thevenin's theorem. It is an analytical method to change a complex circuit into a simple equivalent circuit. It states that any linear circuit containing several voltages and resistances can be replaced by just one single voltage in series with a single resistance connected across the load. Now, look at this figure. This is Thevenin's equivalent circuit where VTH is the open circuit voltage at the terminals, RTH is the input or equivalent resistance at the terminals when the sources are turned off, and RL is the load resistance. Now, in order to draw your new equivalent circuit, you have to follow these steps. First, remove your load and label your terminals A and B. Then solve for VTH. Then solve for RTH by turning off sources. If it is a voltage source, then short circuit. If it is a current source, then open circuit and then draw your new equivalent circuit. Now look at this example problem. If you have a circuit like this is a voltage source of 20 volts which is connected to R1 which is of 80 ohms. It is connected to R2 which is of 40 ohms and it is connected to R3 which is of 60 ohms, and here is your load resistor RL. Now how you are going to draw its Thevenin's equivalent circuit? As you have just read, you have to follow 4 steps. In first step, you have to remove this load and label these terminals A and B. So now this circuit will look something like this. This is R1, this is R2, this is R3, and here you have removed this load resistor and labeled these terminals A and B. This is positive, negative 20 volts. This is 80 ohms. This is 40 ohms and this is 60 ohms. Now in second step, you have to solve for VTH. This VTH is the Thevenin voltage, which is the voltage between these terminals A and B. In this case, as you can see, this is a closed loop where the voltage between these terminals A and B, that is VAB, it is equals to Thevenin's voltage, that is VAB is equals to VTH, and it is also the voltage drop across this 40 ohms resistor as they are connected in parallel. So it can be solved using the voltage divider rule. From voltage divider rule, we know that Vx is equals to V multiplied by R divided by R equivalent. Here this V is 20 volts, this R is 40 ohms, and since R1, R2 and R3 are connected in series, therefore this R equivalent will be 80 plus 40 plus 60. Now after solving this, we'll get VTH equals to 4.4 volts. Now in third step, you have to solve for RTH, which is the value of resistance between terminals A and B. Now in order to find this RTH, you have to turn off the sources. If it is a voltage source, then short the circuit, and if it is a current source, then open the circuit. As you can see, there is a voltage source here, so we'll short the circuit. Now this circuit will look like this. This is 80 ohms, this is 40 ohms, this is 60 ohms, and okay, this is terminal A and this is terminal B. Now as you can see, now this R1 and R3, they are in series with each other, and both of these resistors are in parallel with this 40 ohms resistance. So your R equivalent will be 1 divided by RA plus 1 divided by 40 ohms. Now this RA is the equivalent resistance of these two resistors that are connected in series with each other. So this RA will be 80 plus 60. After solving this, you will get the value of R equivalent. which is equals to RTH, and it is 31 ohms. Okay. Now in fourth step, you will draw your new Thevenin equivalent circuit by plugging VTH, RTH and load resistor. So your circuit will be something like this. This is load resistor, this is terminal A, this is terminal B, and the value of VTH is 4.4 volts and the value of RTH is 31 ohms. So this is your Thevenin's equivalent circuit. Now we will look at Norton's theorem. This Norton's theorem states that any linear circuit with current and voltage sources can be replaced by an equivalent circuit containing a single independent current source and a parallel resistance. Now look at this. This is Norton's equivalent circuit where I Norton is the Norton current and R Norton is the Norton resistance. The main difference between Thevenin's theorem and Norton's theorem is that Thevenin's theorem provides an equivalent voltage source and an equivalent series resistance, while Norton's theorem provides an equivalent current source and an equivalent parallel resistance. Now look at this example problem. If you have a circuit like this is a voltage source of 12 volts which is connected to a 2 ohms resistor. It is further connected to a resistor of 6 ohms. Here is another resistor of 3 ohms and here is load resistor which is of 1.5 ohms. Now if you want to calculate IN, which is Norton current, and RN, which is Norton resistance, you have to follow some steps. In first step, you will short this load resistor. So this circuit will look something like this. Okay, as you can see, you have shorted this load resistor. Now this is terminal A and this is terminal B. This is 2 ohms. This is 6 ohms. This is 3 ohms. Now as you can see, this 6 ohms resistor and this 3 ohms resistor, they are in parallel, and this parallel combination of 6 ohms and 3 ohms is in series with this 2 ohms resistor. So in second step, before finding this Norton current IN, you will first calculate the total resistance, which is 2 ohms plus 6 ohms, which is in parallel with 3 ohms. Okay, it can be rewritten as 2 ohms plus 6 multiplied by 3 divided by 6 plus 3. Okay, after solving this, you will get 4 ohms. So the RT is 4 ohms. From Ohm's law, we know that V is equals to IR. So VT is equals to IT RT. Now for IT, this equation will become VT divided by RT. We know that RT is 4 ohms and VT is 12 volts. Therefore, IT is 3 Now we will find IN by applying current divider rule. From current divider rule, we know that Ix is equals to IT multiplied by Rx divided by R equivalent. Here, as we know that the Norton current is flowing here in this loop, therefore this Rx will be 6 ohms, this IT is 3 ampere that you have just calculated, and this R equivalent will be 3 ohms plus 6 ohms, because in this loop these two resistors, they are in series. Therefore your IN will be 2 amperes. Means after solving this you will get 2 amperes. Now what will you do in next step? In next step you will open all current sources and short voltage sources and open load resistor. As you can see, there is one voltage source in this main circuit and there is your load resistor which you have shorted. It means you have to open this load resistor. Okay, so now I'm shorting this voltage source here, so the circuit will look like this. Okay, the voltage source is shorted. And here I have opened this load resistor. So this is terminal A and this is terminal B. Okay, now this is 2 ohms, this is 6 ohms, and this is 3 ohms. In next step, you will calculate Norton resistance, which is Rn. How you are going to calculate this? Now look at this circuit which you have made in step 3. As you can see, this 6 ohms resistor and this 2 ohms resistor, they are now in parallel with each other, and this parallel combination is in series with this 3 ohms resistance. So your Rn will be calculated by this formula or equation, 3 ohms plus 6 ohms, which is in parallel with 2 ohms. It can be rewritten as 3 ohms plus 6 multiplied by 2 divided by 6 plus 2. After solving this, you will get Rn is equals to 4.5 ohms. Okay. Now, what will you do in next step? In next step, you will draw your Norton equivalent circuit. How? You will connect this Rn in parallel with current source and then reconnect the load resistance. So your Norton equivalent circuit will be something like this. This is your current source, which is of 2 amperes. Now you will connect in parallel Norton resistor, which is having the value of 4.5 ohms, and here you will reconnect your load resistor, which is RL. Now, if you are asked to find load current through this load resistor, how you are going to find this? You are going to find this load current using CDR. So the formula will be IN multiplied by Rn divided by Rn plus RL. Okay, and then if you are asked to find voltage across this load resistor, then you will use this Ohm's law. VL is equals to IL multiplied by RL. you know the value of RL, you just calculated the value of IL from this equation. So this is how you will find your voltage across this load resistor. So this is your Norton's theorem.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.